Yeah, welcome back, everyone. Our first speaker for this session is Biswajit Biswas. Please go ahead.
Hello, everyone. I'm Biswajit Biswas. I'm a second-year PhD student at APC. And today I will be presenting the work that I've been doing as a part of my PhD. And before I begin, firstly, I would like to thank my supervisors and my collaborators from APC and Google Zurich. Without them, all this wouldn't have been possible. And today I will be presenting like a technique that I've been developing to do source separation. In particular, I'll be working on galaxy blending. I'll get to it in a minute. But you can potentially apply it to any kind of source separation problem. But just to give the context of blending, we are heading towards the next generation of cosmological surveys. So we will be observing the sky up to an unprecedented depth and area of coverage. But since we have an unprecedented depth, it means that we will face new challenges. The number of objects that we observe in the sky will increase. So objects that are physically separated, but along the same line of sight, will overlap in the images. Basically, due to increase in the number density of galaxies, we will observe more blending. So in the next generation of surveys, this will become a major problem, and we need to find ways to mitigate it. So I'm trying to obtain the maximum-a-posteriori solution, which you can think of as the best fit solution to the problem. And let's take this for a simpler case where I'm talking about denoising and not deblending. So denoising is where I have just one galaxy and I'm trying to separate it from the background. What I want to obtain is the maximum-a-posteriori solution, which is given by this equation. So it is minimizing the negative log likelihood and the negative log prior. The negative log likelihood is trying to make sure that my predicted image is as close as possible to the input image. And the log prior is telling me that this reconstructed image is actually a galaxy. So these are the two terms that I need to minimize. And if I assume that the noise is Gaussian and uncorrelated, we can simply replace the likelihood term with this. But the problem is evaluating the log prior. How do I tell if my reconstruction is actually a galaxy or not? Traditional classical algorithms use symmetry constraints such as like the symmetry of the light profile and monotonicity of the light profile. But those are not they are very limiting constraints. They don't really capture all possible morphologies of the galaxies. So we will try to find a way around it using machine learning. And before I get to how it's solved, I'll just give a background of variational autoencoders. So it is, you can think of it as a data compression algorithm, and it has three distinct parts: an encoder, a latent space, and a decoder. So when we train a VAE, we are essentially training it to reconstruct this isolated galaxy in the noisy image. So the encoder learns to project the data of the isolated galaxy into a low dimension latent space Z. And the decoder takes a mapping from the latent space to the image space. So it reconstructs back the galaxy. So while training the VAE, we have two terms, a reconstruction term and a regularization term. The regularization term essentially tries to make sure that the latent space distribution has some nice properties so that we can sample from it and generate new galaxies with it. So all the galaxies that we have trained our VAE with is projected to a certain region in the latent space. So you can sample from this latent space and generate new galaxies. So that is only if you know the underlying distribution that the encoder projects it to. Such models have already been trained to generate galaxies. There's some work done by François Lanuz, which is already published. But now I want to use this in my deblending problem. So once again, going back to the denoising, I said that the problem was evaluating the log prior. But now that we have a distribution in the latent space, we can take this problem into the latent space and evaluate a log prior over here. So if I know the distribution from which all the galaxies are sampled from, given each latent point, I can evaluate a probability if it's a galaxy or not. So if I take this problem into the latent space, I can evaluate the log prior. It's just that to compute the first term, the log likelihood term, I would need to map the latent space back to the image space to compute the mean square error over here. So f theta is the decoder that I've already trained. So here I'm not really training the VAE again, it's already trained. So the decoder has learned a mapping from the latent space to the image space. And now I can evaluate this full term. So the objective now is simply to do a gradient descent. I start off with a random prediction for this galaxy, so a random image of this galaxy. But what I'm actually doing is taking the latent space representation and trying to find an optimal solution in the latent space so that it gives me the maximum posteriori. Just one limitation over here is that once the decoder is trained, it's really a fixed size output. So it's 45 by 45 pixels is what I've chosen. And it will become important as we move on to the deblending problem. Now, deblending is, we will think of it in the same terms, except that now we have, let's say, multiple galaxies, and they are overlapping. Now, for each galaxy now, I will need a latent space representation. So I have a set of representations, one representation for each galaxy. And I'm trying to do the same optimization, except that I will try to optimize over all of them at the same time. So here I'm summing over the prediction for each galaxy, like mapping each representation back to the image space and summing over it. So I have a reconstructed field. And then there is the log prior term, which is summing over the probability of each reconstruction being a galaxy. As I said before, that the V has a limitation that the output image is fixed, the size is fixed. So it's 45 by 45 pixels. So what I have to do is I need the detection positions of, I need prior detections of these galaxies, which is not a bad assumption because we, like even Scarlet, which is one of the like state of the art for deblending, assumes that. And given that we are trying to do it for a ground-based telescope, we can also use like information from space-based telescope as prior for detected positions of galaxies. So we can have the detections, the positions of the galaxies. Here we are just trying to separate the fluxes and assign them to isolated components. So now just trying to do the minimization over all the representations at the same time will give me the maximum posteriori solution for the entire field. And just to show you a working example, here I have just these three galaxies. So these are the ground truth, and these are the predicted ones after I have done the optimization. The images are normalized, so you'll see it's like very small values. But after I subtract all these predicted models from my input image, I get the residual, which looks fairly Gaussian. So it seems to be working well. But just to test it on a larger scale, just to make sure that the model is scalable and we don't break down as soon as we get big images. Here I have a simulated input field, and I've taken like a transformation just so that the galaxies are more visible over here. So now you observe that there are a number of galaxies which are blended. So we are trying to solve the deblending problem over here. And after getting the predicted field, I once again subtract it from the input and get a residual. It looks, the distribution looks fairly Gaussian. So once again, but we do observe like some structures. So I won't say it's like perfect, but it is able to get rid of many of the deblending, blended galaxies and solve the blending problem over here. Now, getting to the test data of that was more qualitative. Now we want to do something more quantitative. And I have simulated galaxies using the CATSIM catalog. And here we have the PSF fixed. We are not varying the PSF. And we have we generate these fields, which are 205 pixels, and impose paste galaxies overall in this field, which has a density which is more than that of LSST, because we wanted to have more blended scenes and evaluate the blending algorithm. So the density here is higher than what we like 1.5 times higher than what we expect in LSST. And we generate many such fields and then perform the deblending to get our final results. We have around 90,000 galaxies that we'll be evaluating on. And here I compare it against Scarlet, which is the state of the art, as I said, in deblending. And what this plot shows is the cumulative fraction given a relative photometry error. So I'm summing over the predicted flux with small apertures to get the predicted flux of a galaxy. And I'm doing it for 3 different cases. The first is the blended. So it's the blended scene. I'm not doing any deblending, and I'm just trying to measure the photometry. Obviously we will have high errors, but this gives you an idea of how many of the galaxies are blended and how severely they are affected by blending. We see that Scarlet improves the results quite a lot, but when we use our algorithm, it further improves the results of Scarlet. Another metric that we have used to get our results is the cosine distance. So this is the cosine distance will go closer to 1 if my reconstruction is very close to the actual galaxy, and it will go like towards 0 if there is more distance. So this is how we evaluate the cosine distance. And here again, I'm giving the results for the R band. Just to remind you that LSST will have 6 different bands, and here I'm giving showing the results only for the R band. And we observe that once again, Madness is able to provide improvement in the performance. So just to conclude, we developed an algorithm using VAEs. Well, I didn't talk about normalizing flows, but to get the distribution in the latent space, we have to use normalizing flows or some other density estimate. But that's, well, not, yeah, we can discuss further, but I've skipped it for this talk. And we observe that our performance is as good as the state of the art. But in the next steps, we want to push this into some science pipeline and see what effect it has on science. And also like handle artifacts in the real data, such as decoupling the PSF. So far, I've assumed that the PSF is constant, and we have not tried to decouple. But we can envision a hierarchical model where the neural network is trying to predict the image of the galaxy, and we convolve the PSF on top of it. In fact, that work has already been done by François Lenuz when he was trying to simulate galaxies. So he created such a hierarchical model, which does not assume a fixed PSF model, but imposes the PSF according to different surveys. And currently we are working on the paper to get it published, and the code is available on GitHub. Thank you for your attention, and if there are questions, I'd be happy to answer them.
Yeah, we have time for a couple of questions.
Very nice talk. Looks like a really cool method. I mean, do you have a sense that you might be able to actually extend this to be able to extract unbiased shear from your reconstructed galaxies?
Well, right now, we haven't really pushed it to some science pipeline, but I think that would be like the broader goal of my PhD topic, if we can get some shear estimates. So that would be something to look forward to and something we want to evaluate. Yeah.
Yeah, next question.
I have a very basic question. So how do you calculate the photometric redshift if the 2 galaxies are blended? This is very crucial for your...
Well, yes, that's something we were planning to discuss sometime later on this week. So blending problem becomes very important when we are talking about photometric redshift or science pipelines. And I'm not really an expert in the photo Z, so I don't have a very good answer to that. But yeah, it will be really important to see how it affects photo Zs and how this deblending algorithm is able to reconstruct. Because different algorithms like Scarlet is also doing deblending, and what we observe that the performance is different in different bands because there's different noise levels. So when we are applying the deblenders, turns out Scarlet is actually performing better in U band, which is very noisy. But in R band, where the noise level is much lower, Madness performs much better. So we would also want to evaluate different like deblenders on how they affect the photo Zs and make sure that we do not, the deblender itself is not imposing a bias on the photo Z results. Yeah.
Yeah, okay.
The errors that you showed, like when you tried to reconstruct on a bigger field and so on, it seemed as if places where you had bigger galaxies, you had like larger errors. Do you understand what's happening there?
Yeah, so actually it's like if some galaxies are extremely bright, the relative fraction of the error is really less over there. But if you see just in terms of flux, then the difference in flux is huge. But if you look at the relative term, then the flux, like the relative error is really small. It's just that the galaxy was too bright. So you see like the imprints of the flux in the rest.
So let's thank the speaker.